So we've looked at Boyle's law. Now we're ready to look at Charles's law. It's the next of the simple gas laws. In this gas law, what we're going to do is we're going to be looking at the volume and the temperature relationship of a gas. So what are the two variables that we're not focusing on? Well, it'd be the number of moles, so we're going to make sure we hold the number of moles constant, and we're going to hold pressure constant. The easiest way to do that is with balloons, okay? Because let's just talk about how balloons work, okay? So we have ourselves a balloon, and we tie it off, and inside this balloon is going to be a fixed number of moles of gas. Balloons are flexible, and they will be pushing out against an external pressure of whatever's out in that room. Let's say out in this room is 1 atmosphere. So it's always going to maintain, it's going to shrink or grow in order to maintain a match of the internal pressure to the external pressure. So balloons are great ways to keep the pressure constant. Okay, so what we're going to do is we're going to look at a demonstration at this point and see how temperature will affect the volume. Okay, so we're ready to demonstrate Charles's law. And in Charles's law, we have to have the number of moles remaining constant. So I have a tied off balloon. And we need to keep the pressure constant. We know that whatever's inside the balloon is stretching and contracting to maintain the same pressure as outside. And right now it's at room temperature, which is around 25 degrees Celsius. What I'm going to do at this point is I'm going to get us some liquid nitrogen. Okay, so liquid nitrogen is extremely cold. It's, gosh, I should have looked this number up, but I think it is a negative 190 something degrees Celsius. So we're putting this into this bowl, and that just looks like fun chemistry, doesn't it? And we're going to take this balloon and we're going to put it in the liquid nitrogen. And I'm going to kind of push down on it so that it can get the cold. And we can already see what's happening to the volume of that balloon. But just because it's so much fun, I'm going to pour a little bit more on there. Right on top. Okay, so now the temperature has definitely gone down. We've seen it decrease a whole lot. And we can now see what the volume did as the temperature went down. So I'll take it out and we can look at it. Volume definitely went some direction when the temperature went down. And then the temperature is going to come right back up, and I'll pull it over here a little bit more so it's in the image there. Bring the temperature back up, and we can see that the volume is doing something right along with that. So we've kept the same number of moles, we kept the same pressure, but we've changed the temperature, and you are going to predict what kind of relationship that is. Okay, so we've looked at that demonstration. Now, what was the connection? So I want you to think about what you saw. Was the volume directly proportional to temperature, meaning as one went up, the other one went up, or was one went down, the other one went down? That would be a direct. Or is it inversely proportional? That means as one went up, the other one went down. Choose your answer. All right, I hope you picked A. It was directly proportional, okay? So as the temperature goes down, the volume went down, and it went way down. We saw that that balloon really shrunk as I put it into the liquid nitrogen, and then when I took it out of the liquid nitrogen, it really expanded as the temperature came back up. So that is a direct proportionality. We would say that temperature is directly proportional to volume. But we don't like to work with those proportionality symbols. We would rather work with an equal sign. So to get an equal sign in there, this is what it would look like. Temperature is equal to that constant times volume. Putting the two pieces on one side, we'd have T over V is a constant, or it would be equally accurate to say V over T is a constant. It'd be a different constant, but it'd still be a constant, just flipping it over. So that is, either way you want to look at it, is the way we could describe Charles's law. This would be the useful form of it, or V's over T's. It doesn't matter. And I more typically, when I write it, always put my V's on top and my T's on bottom. I'm not sure why, but it's equally true with the T's on top and the V's on bottom. But that is a direct proportion. How is that direct? It seems like if one on top and one on the bottom, it couldn't be a direct. But if this gets bigger, This has to get bigger right along with it if you're always going to get the same number out. So as one grows, the other one has to grow to give you a constant. If this one doubles, this one better double right along with it to give you a constant. All right, we're going to look at, not right now, later we're going to be working with calculations for this. We're just introducing all of these concepts right now. I do want to look at this graph. This graph and the work with Charles's law is what helped obtain for us absolute zero, or 0 Kelvin. If you were to look along with this graph, and let me step over and actually write on the screen here. If we were to look at this graph and we took a certain amount of gas at a certain pressure, okay, and we measured the volume at some temperature, and we dropped the temperature down, we know that the volume would decrease, and we dropped the temperature down, the volume would decrease, and we drop the temperature down, the volume decrease. At some point, it's going to liquefy, and we can't keep going forever, but if we took this linear relationship and extracted it until it hit the x-axis, it would hit right there. Let's take another sample of gas. Let's say we took half a mole of gas at 1 atmosphere. Okay? At a certain temperature, it would have a certain volume. As the temperature went down, it'd have a certain volume and so forth. At some point, it might liquefy and quit behaving ideally, but we take the linear relationship and follow it out until it strikes the axis and it hits at the exact same point. Doing it for another gas with a different amount and a different pressure, same thing happens, and it ends up hitting that axis right at that point. As volume goes down, it can't go past 0. So as temperature goes down, it can't go past this, right? You can't have less than 0 volume. It makes no sense. You can't have less than a negative 273.15 in the Celsius scale. So what they did is say, let's define that as the absolute lowest you can go. We'll define that as 0 Kelvin, and everything else is positive from that point. So that enabled us to obtain a value for absolute zero. And that would be our mathematical relationship between the temperature in Celsius and the temperature in Kelvin. So there's our formula that we utilize for Charles's law. And I need to make sure you put a circle around this, that you put exclamation points beside it. It is essential that you use Kelvin in any calculations of Charles's law. Why would that be? Kelvin scale is the only scale that we have where 0 is no temperature and every temperature is positive. This equation could not make sense whatsoever if we had and utilized temperatures like, oh, I've got a gas that was at 25 degrees Celsius and I took its temperature down to a negative 45 degrees Celsius. The units would cancel just fine if I put them into that equation. That wouldn't be the problem. But if you have a positive on one side and a negative on the other side, how in the world could there be an equal sign between the two? There's no way. The volume can't do anything to make that work. We need a scale where 0 means no temperature and every temperature is positive from there, and that is why anytime you're dealing with gases, you are going to work with the Kelvin scale every single time.